George Hantzaras, everyone. Please, a round of applause.
Yes, we're so happy you did
Thank you
this
so
for
much
us.
for coming. It is a great honor to introduce you as our next speaker, who is a distributed systems expert and a hands-on engineer leader with focus on delivering enterprise cloud services at scale. Director of Engineering at MongoDB, focusing on implementing cloud-native technologies at enterprise scale. And the speech will be Kubernetes Operations and the future of cloud-native DevOps. So I guess, George, the floor is yours.
Thank you,
Thank you
George,
so
again.
much.
We're good to go. Hi, everyone. Welcome to this talk about the value of Kubernetes operators when implementing DevOps in cloud-native environments. I'm George Hantzaras, an engineering director at MongoDB, leading Mongo's effort to support Kubernetes. So at MongoDB, our teams are building operators that enable our users to deploy and manage MongoDB in two ways: self-hosted in Kubernetes using the enterprise and community operators, or using the Atlas Kubernetes operator, which is designed to manage and configure Atlas, the Atlas data platform, and we're going to talk about the two differences today. A lot of what we'll talk about today comes from enabling platform teams to build internal developer platforms. That's one of the big goals we have by extending Kubernetes using Kubernetes operators. And you'll be able to find a few of those recipes in an upcoming book coming early next year called Platform Engineering in Practice with Pact. So today my presentation comes with two main goals. Firstly, to help you understand the value of Kubernetes operators in DevOps and platform engineering. And secondly, and probably the most important thing, to be fast and try and take you to lunch as early as possible. So we're going to cover a few things today, and to try to keep it interesting, I'll be alternating between theory and practice. We'll present some context and considerations specifically. We'll question a bit of what Kubernetes really is, how it can be extended using custom resources backed by custom controllers, and how the operator framework comes to help us do that much easier. And finally, moving into practice, we'll see a demo of our own use case at MongoDB and how you can use those operators. So before we dive into the topic, I'd like us to get aligned on what we mean when we say cloud native. It's a much used term, and every time we hear it, it has a slightly different meaning. Cloud native is a software approach for building, deploying, managing software, modern application in cloud environments. To do so, we use modern tools, techniques that inherently support application development on cloud infrastructure. So with the term cloud native, we refer to services that satisfy a few different requirements. So first off, we want our services to be massively scalable and in a dynamic and independent fashion. Automation plays a critical role in cloud native. Infrastructure is treated as ephemeral. We use an API-first approach to communication between our services. And finally, we often see microservices, serverless, and architectures that are based on domain-driven design. And what is the result in our DevOps practices? How is this affected? So first off, we need infrastructure that can support a multitude of architectures, as we saw, containers, functions, and so on. Orchestration is really important because we want to scale and manage multiple services. Rapid releases are powered by highly automated pipelines. Infrastructure as code for automating our infrastructure management. And finally, the ability for developers to self-serve in our infrastructure in order to reduce the wait time and eliminate bottlenecks. So through the rest of the presentation, we'll explore the role of Kubernetes to enabling those. So as I cannot move around and keep you awake, let's play a little game. Yesterday night, I asked ChatGPT what Kubernetes is, and I got a few different answers. So raise your hand if you agree that Kubernetes is a container orchestration platform. Good, that's not wrong. If you think it's a platform for managing software operations, it can be. What if we say that it's a scalable and automated deployment tool? Okay, good. You get the drill. What if we say it's a multi-cloud and hybrid cloud enabler? Cool? In reality, what we say nowadays, and none of these are wrong, but what we usually say is that the way that how Kubernetes has evolved is that it's the platform for platforms. So Kubernetes architecture is based on highly extensible interfaces, which offers a high level of extensibility and customizability. Some examples are the CNI interface for networking, the CSI interface for storage, and even the CRI for runtime interfaces. Now, looking into the Kubernetes architecture and focusing a bit on the control plane, we see that the control plane consists of a few different core components. Amongst other things, we can see the controller manager. The Kube controller manager it's a daemon that embeds the core control loops shipped with Kubernetes. So in Kubernetes, a controller is a control loop that watches the shared states of the clusters through the API server and makes the changes needed to move the current state of the cluster to the desired state. We have multiple controllers that ship with Kubernetes today. We have the replication controller, endpoint controller, namespace controller, and so on. So in a typical Kubernetes cluster, the Kube controller manager runs controllers in what we call a reconciliation loop in the control plane. So each controller is responsible for managing a specific part of the cluster's behavior. And the controller manager runs the control loop and allows each controller to run by invoking the reconcile function. Kubernetes comes out of the box with a few of those that map to the known Kubernetes constructs, such as the deployment or the job controller and so on. Are you confused enough yet? OK, let me try a bit harder. So this is the Kubernetes API structure. And if we look closer, we see two different resource types. And we're going to try to focus there, because if we focus on the whole thing, that's going to be harder. We have either built-in resources, which are pods, deployments, and the stuff that we are all familiar with. And we also have custom resources. And those can be anything that we need to help extend Kubernetes to manage our own services logic. So a custom resource definition gives you the ability to extend the API, whether it's with an operator or without. You'll learn in a bit what an operator is. And using a custom resource definition, we can extend that and provide the additional functionality. So the API extensions is the API that we use for this. It's an API out of the box that has one purpose, which essentially is to give you the ability to extend the Kube API. The custom resource definition object exists to give you the ability to create those API endpoints. So let's see what happens when we use an operator to manage a custom resource. So an operator is designed to build into Kubernetes the management logic for tasks that a human operator managing a service would be doing. It's not there to make production engineers disappear, but to help them automate those operations. On a high level, the operator goes through the following steps. So initially, the user creates or modifies a custom resource. The operator picks up the change through a change event, and through the Kubernetes API server, reads the current state of the cluster for this specific resource. And as a final step, it makes the necessary changes to align the cluster state with the custom resource definition. Necessary changes, again, can be coded and can be anything that we want. It can include redeploying, reconfiguring, scaling, and many more. The Operator SDK was introduced as a tool to help us streamline the development of operators, and it's nowadays pretty simple to do so. So we have the Operator SDK that helps us create a new project. We just define the custom resources that we need in our API to extend the API. As a third step, we define the controllers to watch for reconcile resources. write the reconciliation logic, and that's where you can, this is an arbitrary thing, you can add anything you want there, anything that your application needs in order to be managed. And then build and generate the operator deployment manifest, and build the operator image, push it to a registry, and distribute and deploy. So it's a pretty straightforward process, and the operator SDK makes it pretty easy. Now, when the operator is deployed, it creates a custom controller, which is responsible for deploying the application. And the reconcile loop of that controller watches and heals the resources as needed. So returning to the slide from earlier, we can now start understanding the role of operators in DevOps. So the animation is not playing. Ta-da. So first off, it helps us extend Kubernetes to support multiple workload types, like serverless, functions, databases, and so on. Kubernetes operators help us build management logic into our cluster, making deployment and delivery of services much easier, as well as day two operations. Operators can manage also external resources, external service providers. So this provides a unified infrastructure as code language for all of our infrastructure. We're going to dig a bit deeper into that. And finally, we can provide self-service capabilities for developers using our services. We usually see two different types of operators. The first is designed to manage resources that are running in Kubernetes, that are deployed in Kubernetes. This is more or less the original design behind the custom controllers. And the second type of operators use Kubernetes native way to manage resources that live outside of our cluster. This can be cloud providers, this can be SaaS services, anything you want. This is pretty similar, as you can understand, to using an infrastructure as code tool. So in our case, we've categorized these two different operator types. We have, on the one side, we have the community and the enterprise operator that manage resources running in the Kubernetes cluster. And we also have the MongoDB Atlas operator, which manages cloud resources in our Atlas developer data platform. In the first example, the MongoDB enterprise operator is of the first type, and manages resources that live in Kubernetes, in our cluster. So we can see here is just an example of what the operator deploys. Initially, it creates a secret with the configuration for the database deployment. And then it creates a stateful set for the application database, which is backed by a persistent volume. As a third step, it deploys a stateful set, which is the Ops Manager, which is the management service of our databases, and so on. As you can see, we deploy multiple resources. We have optional resources as at the top right. So if you enable backup, you can deploy another stateful set backed by another persistent volume, and so on. So for the second type of operators, we can use, as an example, the Atlas Kubernetes operator. So this operator helps ensure that the states of projects, clusters, databases, users in Atlas matches the configuration in those custom resources. So we have our smart user over there. He has decided to manage the resources through the Atlas operator. That's what makes him smart. He deploys manifest either through Helm charts or kubectl, and then the Atlas operator reads those and interacts with the Atlas admin API to make those changes to the Atlas platform. So as we said, this seems a lot like infrastructure as code. So why someone would prefer this versus Terraform, Ansible, or anything else? So first off, an operator does what we call continuous reconciliation. So this helps us fight infrastructure drift over time. Second, using this module of having two types of operators, we manage both everything that is running in Kubernetes and everything else. So we have one unified approach to infrastructure as code. We have only YAML for our developers to deal with and not multiple different types. And finally, the operator can integrate with all available CNCF tools and extend its functionality. So that was all with the slides. Let's see some demos. So for the demo, we'll be using, I lied, this wasn't all of the slides. So we'll be using two operators. We're going to use the Atlas Kubernetes operator and the Argo CD operator. And our journey is going to be split in three parts. So first, we'll deploy and manage Atlas resources through the Atlas Kubernetes operator. Second, we're going to automate this process using a GitOps approach, using GitHub and Argo CD. This way, we make it self-service. We make the first part self-service and easy to use with templates and make it scalable. So GitOps allows us to use our Git repository as a starting point of deploying infrastructure changes and as a single source of truth. So then a tool like Argo CD, it can be Flux, it can be anything we want, is responsible for taking the files stored in the repository and applying changes to our Kubernetes cluster. And lastly, we're going to show how easy it is to connect applications to our deployed database, only using Kubernetes secret, and that shows how easy it is to deploy new application and so on. So we have multiple ways to install the operator. Most operators can be installed via either kubectl, Helm charts. In this case, we use the Atlas CLI, mainly because besides just installing the operator in our cluster, it also manages the configuration. So we start by running the Atlas Kubernetes operator install command. And this does two things. Firstly, installs all the operator manifests in our Kubernetes cluster. And it also creates, first off, we can see the operator has been installed. And it also creates a secret that contains our API key that the operator is going to use in order to interact with the Atlas API. Now that the operator is installed, let's create our new project. A simple YAML file as any other Kubernetes resource. We just use kubectl apply, and we see that in our cluster, the new resource has been created. And then under the hood, the operator has picked up the change in the resource, and through the Atlas admin API, has created the new project. Now we create a cluster in that project. Again, a simple YAML file. We have anything that we would have through the API. We define the cluster, the instance size, the provider, the region, anything that we want, all the parameters for our cluster. Same thing, kubectl apply. And the Atlas deployment has been has been created as a custom resource. And we see in our project, it is now being deployed in Atlas. So using the operator enables us to manage Atlas in the same way that we would manage an application, a service that is running in Kubernetes, but that doesn't solve all the problems that we saw before for cloud-native DevOps. First off, complexity at scale. If we enable many engineers building many services, we need tooling that scales and standardizes across teams. Rights and permissions, you probably know that giving everyone rights to directly manage services on production Kubernetes clusters isn't always the right thing to do. And using a GitOps approach is going to help us reduce the access rights needed. So through GitOps, all you need is access to the right repository, and Argo CD does all the rest. And finally, without self-service and automation, a lot is being done manually. and every engineer has to learn how to do it. So let's see how we can go beyond infrastructure as code stored just in repositories, but also we can have centralized clusters enabled with Argo CD and provide the level of automation for large-scale organizations. So first off, we're going to start by installing Argo CD, and for that we're going to need a namespace where all components are going to be installed. The Argo CD operator installation is automated through a simple script. It's just a few seconds and one command. And we can see here that all of the operator services are running in the Argo namespace. Now, the next step is we need to create an Argo CD application. We call it a DBAS application. And what we define is which repository we want Argo to watch and which destination cluster we want our resources to be deployed. And again, we apply this. And going into the Argo UI, we can see that our database as a service application has been created. Now, we go back to the editor. We're going to use the same project definition as we did before for the Atlas project. We've only changed the name. But instead of applying to Kubernetes, we just push. And what has now happened is that we can see that Argo has picked up the change. So we see the new GitOps project has been detected in our Git repository and now has been deployed by Argo in our cluster. And then as before, the operator picks up, and through the Atlas admin API, creates the new project in Atlas. Same for the cluster. We just changed the name. Everything else is the same. Git push. And we can see in the Argo UI, we see the new resource detected. And we see that this has now been created by the operator, is being created by via the Atlas admin API. One second. Cool. So now we've streamlined the deployment and management of new databases. So let's see how easy it is to spin up new applications and connect to those in a Kubernetes native way. So here we'll be using a new resource called Atlas Database User in order to manage database access. Each Atlas Database User is just another file in the repository. The operator makes managing them easy. So here we've already created the secret for the user password. And we have a custom resource definition, creating a new database user using this password. As before, we push to Git, and Argo CD and the operator automate the whole process. Besides creating, we can see here the GitOps user has been created. But besides just creating the Atlas database user resource, we see that the operator also creates a Kubernetes secret. And this, if we inspect this secret, we can see that this contains all the connection strings and all the data that our applications are going to need in order to connect to our database. Now, for the last part, we just create an Kubernetes deployment. We use the MongoDB image, and we deploy a Mongo shell referencing the Kubernetes secret we just created. We deploy our new deployment. And we can now inspect the logs of this deployment and see that it has connected to the Atlas cluster. Now, this was the end of the demo, and usually at the end of the demos, we're expecting fireworks towards the end, but the good news is that we're talking about managing infrastructure in critical production environments, so the good thing is when we don't have fireworks. So after building our first operator, there are many things that we've considered as next steps and we've implemented. First up, distributing an operator. You can either develop an operator to streamline your internal operations or for the ease of use of your customers. OLM, the Operator Lifecycle Management, helps you distribute and automatically upgrade and manage an operator. Operator capability levels describe the maturity of an operator. Level 1 is basic installation. Level 2 is seamless upgrades. Level 3 is full lifecycle management. Level 4, deep insights. Level 5 is called autopilot, when you can auto-scale, tune, and auto-configure an application through the operator. And then building operator that manages other operators. We see that lately more and more. As an example, we have two different operators. We have the Atlas and the Enterprise operator. One deploys MongoDB in the cloud and the other on-prem. The idea there is to build a generic Mongo operator where the developer doesn't really care where resources are deployed. He just asks for a database, and magically everything happens in the background. And finally, building operator that manages resources across multiple Kubernetes clusters. This helps for better scalability, resilience, compliance. This is a very interesting topic and a very active topic in the CNCF community at the moment. We dedicated the whole presentation at KubeCon for this 2 days ago. It was so interesting that leaving the stage, I hurt my foot. And that's it. We have this QR code and the link. You can find all the information about the demo you saw today, and it describes how you can build a database as a service on Kubernetes using Argo CD and the Atlas operator. And I think we have a few minutes left for questions. Thank you.
Thank you so much. Considering your issue here with your leg, hope you heal fast. Okay, great. Thank you so much. That was very insightful, giving us a perspective of a very successful company utilizing Kubernetes for infrastructure as a code and automation and scaling and all the advantages that you can get from that, from a unified approach, of course, also, so of managing everything. So yeah, that was very interesting. Let's see if we have questions. Okay, wow, there's one with 8 thumbs up points here. Okay, let's see that. How do you envision Kubernetes operators influencing the automation and management of cloud-native applications in the next 5 years, particularly in terms of enhancing scalability, reliability, and security? So we put in the aspect of information security on this topic, which is interesting.
Yeah, I would say the two probably most important trends at the moment, first off, is multi-cluster. We see operators that manage resources spanning multiple Kubernetes clusters. That is one that's gaining more and more traction, and it's a topic that's gonna, over the next at least 2-3 years, it's gonna be really important. And also on the aspect of security, we see a lot of awareness around supply chain security. So there are, I believe there are going to be a lot of solutions that are going to arise there. There are a lot of problems to solve. Essentially, an operator extends the core functionality of your infrastructure, so it has a lot of capabilities to do a lot of harm if not securely built. So that's an important part of it.
Yeah, and it makes sense, data governance and who has access to what data and it's also key, and I guess your point being that, yeah, we need to resolve security issues while we're coding.
Yep.
Okay, great. So
Are there any challenges on using Kubernetes?
a more general
Well,
question.
Kubernetes is not easy. And
To deploy, you mean?
nothing is easy. Kubernetes is only easy when you start, and then when you get lured in, it's very hard. So, jokes aside, Kubernetes has a lot of complexity, especially in the networking side, where you really have to understand what's happening under the hood.
Yes.
And we see a lot of people using managed services like EKS, AKS, and
Right,
so on.
right.
And if you don't know what's happening under the hood, then when something goes wrong, it's really hard to troubleshoot. So
That's a
it's an
very-
extra layer
very
of
good
significant
point.
complexity which you have to be
But
familiar
also
with.
security.
Yeah, of course.
Yeah, true. Okay. Okay, great. I think you have time to rest now. Thank you
Thank you.
so much for standing here for half an hour, guys. Yeah, really worked.